Hi everyone, welcome back. Today we will be deep diving into the attention mechanism. We'll explore how it overcomes the sequence to sequence model limitations and demonstrate its impact on the machine translation, NLP, and deep learning. So let's get started. Now I want you to buckle up because in this from here onwards, we would be understanding the technical details as well on what goes on into creating these models, what are the technical stuff that are, what happens under the hood basically. So this might start getting a bit tricky. I'll try to keep it as high level as possible, but we'll also keep it for the technical audience from here on. So let's get started. Now, why did the sequence to sequence model struggle, right? The sequence to sequence model had revolutionized machine learning translation, but they had one major flaw, which was information bottlenecks. The encoder compasses the entire sentence into a fixed length vector. But what happens when the sentences are long and complex? Then the key details will get lost, right? So now how does an AI determines which word to focus on while translating? And how can a model prioritize crucial words without losing its context? So this is where the attention mechanism came into play, right? The problem with the context vectors in the sequence to sequence was that these context vectors had some kind of bottlenecks, where either the sentence is compressed into a single vector or it has a vanishing context issue as well. So for long sentences, what would happen is the decoder still struggles to retain important informations from earlier in the sequences. So example of a bad translation without the attention would be: the boy who lived in a small village near the mountains and loved to paint disappeared yesterday. So without the attention, the incorrect translation would look something like: लड़का जो एक छोटे गांव में रहता था गायब हो गया. So it's losing a lot of details, right? For example, near the mountains and love to paint. It doesn't has the attention span to basically grab these kind of details. So this is where attention fixes by dynamically selecting the most important and relevant words at each decoding steps. Now, let's try to understand what the attention mechanism is, right? So the attention mechanism allows the decoder to focus on important parts of the input sentence for each decoding step rather than just relying on the compressed vector. So the key idea over here was, instead of storing everything in one static context vector, the decoder assigns a dynamic importance to each word in the input sentence. So the attention weights, the higher the weight is given to a word, that means that is more relevant to the current step. Let's try to break it down step by step on how exactly does the attention mechanism work. Now, the mathematical formula of the attention mechanism is it's divided into 4 steps. The first step is computing the alignment scores. So for each decoder step, time step t, the computation of the alignment, which is et of I, between the decoder state ht and each encoder state hi, is denoted by this common scoring formula. Although this is the common scoring formula, there were some alternative scoring formulas as well which were used, and these formulas included dot products, additive, also known as Bahdanau, or scaled dot product, also known as Luong. Now, I'm sorry if my pronunciation is wrong, but these were the alignment scores these were the some of the alignment scores which were used to calculate. So these were the formulas of the alignment scores which were used to calculate the scoring functions, or the alignment scores. Now, the second one was the compute attention weights. Now these alignment scores were converted into probability scores using softmax functions. Now, if so, for example, if alpha ti is 0.9, the word hi is crucial for decoding t. And if alpha ti over here is around 0.1, then the word hi is less relevant. So that's how the weights, the attention weights were given to each individual words, which are denoted by hi. After that, there was a weight context vector. Now, which is basically denoted by this formula. Now the new context vector CT is the weight sum of the encoder states, right? So this context vector will adapt dynamically at each time step. And then finally, there was the prediction step, where the decoder, so this is your final prediction step, where the decoder uses both your CT and your HT to generate the next word. This ensures that the model attends to the most relevant words per step. So this is what makes attention's translation more accurate and preserve long range dependence. Now let's understand this with an example. If I could just pull the example. Okay, here it is. Now suppose I have an example sentence for translation where in English I have something like I love eating food, especially butter chicken, and in Hindi I have a target sentence which is मुझे भारतीय खाना पसंद है विशेष रूप से butter chicken. Now without the attention, the model encoders would take I love eating Indian food, especially butter chicken, create a context vector out of it, and then the decoder layer will generate something like मुझे खाना पसंद है, which will lose the importance of Indian, especially butter chicken, and those kind of words, right? And the translation will remain incomplete. But with attention, the decoder at मुझे attends to I and love, the decoder at Bhartiya attends to Indian, and the decoder at butter chicken will attend to butter chicken itself. And that's how the translation will now retain all the important informations or all the important words which are present in the particular sentence. Now let's try to understand the variants of the attention mechanism itself, right? Now we just touched based upon these Bahdanau attention, Luong attention, and the self attention. But I'll quickly skim through what exactly did this three type of attention were basically, right? So the first one, the Bahdanau attention, was basically additive attention, which computes alignment score with a small neural network. So it was used in early sequence to sequence model where it used something like RNNs plus LSTMs. And then Luong attention, which is multiplicative attention, it used something like dot product for scoring or dot product scoring for efficiencies. Now this was basically or majorly used for neural machine translation models. The self attention, of course everyone knows about it, are used in transformer models where it is also known as scaled dot product attention. And instead of focusing on encoder state, the self attention allows the word to attend to all the words in the same sentences. So for example, in BERT or GPT, the word bank can now attend to the nearby words to decide if the meaning is river bank or the financial bank. So this is how the self-attention was used as a foundation of the transformer models itself. Now, why the attention model revolutionized NLP? Because there was no information bottleneck. The AI can dynamically attend to relevant words at each step instead of relying on one compressed vector. Also, it had better performance for long sentences. Unlike the traditional RNNs, the attention-based models can handle long-range dependencies. And these were, of course, then the foundation of the transformer and the LLM models as well, where you will have transformer-based models such as BERT or GPT extend the attention mechanism to work in parallel rather than sequentially like in RNNs. So this allowed for parallelization of training the network itself. And without the attention layer, we wouldn't have models such as GPT or BERT or the modern AI powered translation architecture. Now, attention changed everything. But what if I told you that there's even a bigger breakthrough? The transformer model took attentions to the next level and completely replaced the RNNs. In the next episode, we will break down the transformer architecture, the model that powers ChatGPT, Google Translate, and modern AI. So please don't miss it. Share it with someone who might love it.